Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifbut.me. The other way is to download all the notebook files from course GitHub account arifpucit, and all the notebooks of this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for the lecture number 6.7 of the 6th module, overview of machine learning, for the course titled Tools and Techniques for Data Science. Well, my dear students, if you are following this series, then in the previous 6 sessions, we have covered the basics of simple and multiple linear regression using the NumPy library and then using the scikit library. Before moving on to the advanced concepts, I'm switching gear and have decided to give around 4 or 5 sessions on data pre-processing and feature engineering. And this is the first session in which we will practically see different techniques to identify and handle outliers from our dataset. So let's move on to the learning agenda of today's session. We will start with the overview of data pre-processing and feature engineering. We will practically understand z-score, IQR and percentile methods to identify the outliers, and then we'll learn different techniques to handle these outliers. Well, these 3 methods fall under the univariate analysis category, and I will also touch upon one or more multivariate analysis techniques to detect the outliers. So let's move ahead and start playing. My dear students, we have talked about data pre-processing and feature engineering in our first session of machine learning as well. And these 2 terms are used interchangeably. However, you can think of data pre-processing as making your data ready to be fed to the machine learning model, while feature engineering is the process of using domain knowledge to extract features from raw data via data mining techniques. We normally perform these 6 tasks during the data pre-processing and feature engineering phase: detecting and handling outliers, missing values imputation, encoding categorical features, feature scaling, extracting information, and combining information. I intend spending around 4 sessions on exploring different techniques to perform these 6 tasks. Today we will explore different techniques as to how we can identify outliers from our dataset, and once identified, how to deal with them. So, first of all, let me define an outlier. Well, statistically speaking, an outlier is a data point that differs significantly from other observations. The value of an outlier is very much domain dependent. For example, if you are considering the age column in a dataset, then probably any value above 100 years can be considered as outlier. Similarly, if you are considering the monthly salary of an IT expert in Pakistan, I think any value above 1 million Pak rupees can be considered as an outlier. My dear students, we all know that every data science project starts with the collection of data, and that is where outliers are actually introduced in your dataset. An outlier can be a result of a mistake during data collection, in which case it must be handled appropriately. At the same time, an outlier can also be a real exception, which is just an indication of variance in your data. And remember, my dear students, in case of if your machine learning model is going to detect anomalies, for example, a bank fraud in a banking transaction, then you must not remove the outliers from your dataset, as this is what your machine learning model will be looking for later. And one more thing you need to keep in mind is that all distance or weight based machine learning models like linear and logistic regression, k nearest neighbors, and support vector machine are sensitive to outliers. However, outliers do not have much impact on tree based algorithms like decision tree and random forest. Well, my dear friends, there are a dozen of techniques that you can find in literature to identify outliers. I have divided them into two categories: the univariate analysis and multivariate analysis. In univariate analysis, we only consider the variable under consideration, while in multivariate analysis, we consider more than one variables to identify the outliers. Uh, in today's session, I will discuss three univariate techniques to identify the outliers. The first will be the z-score method. If the data under the column under consideration is normally distributed or is close to normal distribution, we will use this z-score method. On the contrary, for skewed data, which is not normally distributed, we will either use the IQR, that is interquartile range method, or the percentiles method. Finally, I will also use a scatter plot to analyze the input feature and its relationship with the output label to identify the outlier under the input feature column. My dear friends, once we have identified the outliers in our data set, let's suppose from under one column, the next task is how to handle them. Once again, there exist a bundle of techniques in literature, but we will be using two out of them. One is trimming, in which we actually remove the rows having outliers. The limitation of trimming is that if there are a lot of outliers, maybe more than 20 or 30%, those observations will be removed from your data set, which of course you will not like. The other technique is capping, in which instead of removing the row altogether, we assign a boundary value to all the outliers. This capping technique is also known as winsorization. A third technique to deal with outliers is discretization, where you make brackets of your numerical data. For example, let me give once again the example of an age column. You make brackets of ages like infant, toddler, teen, young, adult, and old. This way, the outliers will be merged in the initial and the last pin. Okay, so now we have a fair idea at an abstract level what outliers are, the techniques to identify them, and the techniques to treat them. Let's move ahead and practically do this on sample toy dataset for crystal clear understanding. And let us start with the first method, and that is a z-score method to identify outliers. Well, before applying this technique, make sure that the data under the column is almost normally distributed. And this histogram shows the distribution of a hypothetical ages column. And you see it is normally distributed. The mean, median, and mode are all the same, represented by this yellow vertical line at the age 30 years. The distribution is symmetric about the mean. By that I mean half of the values fall below the mean and remaining half fall above the mean. Moreover, this distribution also follows the empirical rule, that is 68, 95, 99.7 rule, which says that 68%, 95%, and 99.7% of the values lie within 1, 2, and 3 standard deviations of the mean respectively, as shown in this image. So my dear students, any value under a normally distributed column greater than mu plus 3 sigma or less than mu minus 3 sigma can be considered as an outlier. Or we can say that if the z-score of a value, that is xi minus mu over sigma, is above plus 3 or below minus 3, then that value can be considered as an outlier. Great. So let's do this practically. In this code cell, I'm importing the required libraries and loading a CSV file containing an artificially generated hypothetical dataset into a pandas data frame named df using read underscore CSV method. So this dataset has 10k rows with two input feature columns x1 and x2 and an output label named y. Okay, so before identifying the outliers, let me call this info and describe methods on this data frame. So none of these columns has a null value, and these are the statistical measures of the three columns. Let us now draw the histograms of the two input columns x1 and x2. Well, in this first line, I'm calling the subplots method of the pyplot module of matplotlib, and it is returning a figure and a set of subplots, axis objects. Then I'm calling histplot method of seaborn twice. Once on the x1 column of the data frame and then on the x2 column of the data frame. Note the axis argument at the end. Let me execute it. Great. Note the values under the x1 column in this blue histogram are uniformly distributed, while the distribution of values under the x2 column are left skewed. This means we can apply the z-score method to identify the outliers on the x1 column only. Okay, let's move ahead, and over here in this code cell, I'm calculating the mean, standard deviation, minimum and maximum values of the values under the x1 column of the data frame. Moreover, I am using the figure level displot method of seaborn and passing it the kind argument as histogram. At line 11, I'm also drawing an orange color vertical line at the mean location using the AXV line method of pyplot. And this loop which I have highlighted, I am using this to draw 6 vertical lines of red color at mu plus 1 sigma, 2 sigma and 3 sigma, showing the empirical rule. I hope this code makes sense. Let me execute it. Great. So you see the mean is around 30. The standard deviation is 10. And almost 99.7% of the data falls within 3 standard deviations astride the mean. That is between this something close to 0 and this age of 60. Great. Okay, I think we are now equipped with the knowledge to identify the outliers. Let me use the option 1. We simply locate those rows of our data frame where the value under the x1 column is either less than mu minus 3 sigma or greater than mu plus 3 sigma. So this code cell compute the lower and the upper limit values, which comes out to be minus 0.2 and 60.04. Well, this line of code in this cell will return only those rows of the data frame where the x1 values are greater than the upper limit. So these are the 7 rows or observations where you can see x1 column has a value greater than 60. Similarly, this line of code will return only those rows of data frame where the values under the x1 column are less than the lower limit. Great. So you see there are roughly, I think, 11 rows where you can see under the x1 column the values are less than zero point 0.2, which was the lower limit. And finally over here I am just ORing the two conditions, combining the above two conditions using the OR operator, and of course this will return us the I think 18 rows where we have outliers under the x1 column. The values are either greater than the upper limit or less than the lower limit. Good. The other option is quite similar, that is identify the outliers using the z-score value. For this we calculate the z-score of all the values under the x1 column. Uh, okay, so this I'm just calling the copy method of the data frame, which will of course create and return a deep copy by default of df in a new data frame df1. In this line, line number 2 over here, I'm just using the formula. I'm just creating an additional fourth column, that is z underscore x1, whose values are the z scores of the corresponding values under the x1 column. Let's execute. So this is the fourth column that I've just created containing the z score values. This z underscore x1 column has the z score values of this x1 column. Fine. Now to identify the outliers, it is a piece of cake, which naturally are those rows in this new data frame where this z underscore x1 column has values either less than -3 or greater than +3. So this is the mask which is passed to this data frame where the values under this column are either less than -3 or greater than +3. And of course this will also return the same 18 rows which were identified using the option 1. My dear students, now we are done with identifying or locating the outliers. The next question is what to do with them. As discussed before, there are different techniques, but we will use trimming and capping for the time being. Let me do trimming first. And trimming is a technique where we simply trim or remove the rows having the outliers. And we use this technique when a lesser number of outliers are there. Since in our dataset we have a total of 10k rows and just 18 outliers under the x1 column, so I think it is safe to trim. Well, this is the line of code where I am using this technique. This is the mask I am using. Just keep a note of this AND operator and the comparison operators, which are also negated. While detecting, we use this less than and greater than, and over here we are using less than equal to and greater than equal to for the upper limit and lower limit, and we have changed the OR operator with the AND operator. So let me execute it. Great. So this has returned just 9,982 rows. The 18 rows have been dropped from this new data frame. I hope this makes sense. Okay, so we can remove values using this z-score as well. So for that, I'm using the df1 that we have just created above. We simply need to drop those rows from this data frame where z underscore x1 column has a value less than -3 or greater than +3. So this is the line of code which is doing this job. It's more or less the same logic as used in option 1. Let me execute it. So once again we have 9982 rows. The 18 rows have been dropped. But this time of course we have an additional column which we can always drop using the drop method. Great. So this is the new data frame in which all the 18 rows containing the outliers corresponding to the x1 column have been dropped. So we are done with trimming of the rows having outliers. Let's do the capping as well, where instead of removing the rows, we assign the two boundary values to all the outliers. A very elegant way of doing this is using the where method of NumPy library, which is passed 3 arguments. So this is the first argument, which is the condition. If the condition evaluates to true, the second argument is returned. And if this condition evaluates to false, the third argument will be returned. And in case of third argument, I have another where clause. Let me describe it once again. So after creating a deep copy of the data frame, I'm using the nested where method. I'm using a where inside where. This first where method says if the value under the column x1 is less than lower limit, return lower limit, else move to second where. And this second where says if the value under the x1 column is greater than upper limit, return the upper limit, otherwise return whatever value is there under column x1. Simply speaking, this line of code will override the outliers under the x1 column in this capped underscore df data frame with either the lower limit value or the upper limit value that we have calculated above, that is -0.2 and 60 respectively. Let me execute this. And note this new data frame has all the 10k rows. The only difference is that all the values below -0.2 are replaced with -0.2 and all the values above 60 are replaced with 60. And to verify, of course, you can use the min-max value. You can use describe on this capped df. You can see the min value is -0.2 and the max value is 60.04. So the outliers are no more there in this new data frame. Great job done. Okay. Well, my dear students, we are done with identifying and handling outliers using the z-score method. Let us now talk about the second method of identifying outliers, and that is using the interquartile range. Well, we have discussed this in detail during our descriptive statistics video session, I think. But let me give a quick recap about IQR and box plot before using this technique practically on a toy dataset. Well, my dear students, quantiles, quantiles, Q-U-A-N. Quantiles actually divides a distribution into n equally sized partitions. A two quantile is called median, which divides a rank ordered dataset in two equal parts. Four quantile is called quartiles, which divides a ranked ordered dataset into four equal parts. 10 quantile is called deciles, and 100 quantile is called percentiles, and so on. Right now we are interested in quartiles, Q-U-A-R, which is described in this image. The first quartile Q1 is the same as 25th percentile. The second quartile Q2 is the same as 50th percentile or median. And this third quartile Q3 is the same as 75th percentile. And interquartile range IQR can be calculated by subtracting the third quartile from the first quartile as shown in this formula. My dear students, unlike range of a dataset, IQR is not sensitive to outliers, and therefore it is useful in identifying those outliers. And this is done by setting up a fence outside Q1 somewhere over here and outside Q3 somewhere over here. And any data value that falls outside this fence is considered as an outlier. I hope this makes sense. Okay. Now turning over to a box plot. My dear students, a box plot is a method that is used to graphically represent numerical data through their quartiles. And this image is a box plot representing a hypothetical dataset. This blue box in the middle represents the IQR, interquartile range. The two vertical lines, this one and this one, astride this blue box are also called whiskers, just like the mustaches of a cat. This lower or left whisker of a box plot is 1.5 times IQR below Q1, while this upper or right whisker of box plot is 1.5 times IQR above Q3. In case of a normally distributed dataset, the lower whisker is mean minus 2.698 sigma times this sigma is actually the standard deviation, and this upper whisker is mean plus 2.698 times this standard deviation. And all the values which are beyond these two whiskers are considered as outlier by the box plot. And you can of course increase the value of these. Instead of using minus 2.698, you can use 3 sigma over here as well as 3 sigma over here. And if you closely observe this particular box plot, there are quite a number of outliers on the right represented by these dots over here. And moreover, you can also see that this box plot is quite shifted towards left, showing that the overall distribution of this dataset is left skewed. Okay, enough. So let me once again load this dataset, the same old dataset. And let's identify the outliers using the IQR method this time. Once again, we have two columns, input features x1 and x2, and the output label y, and the dataset has 10k rows. Once again, let me visualize the two input features, x1 and x2. You see the x1 is normally distributed while x2 is not. We have used the z-score method to identify the outliers in under the x1 column. And this green histogram shows that the distribution of the data values under this x2 column, this is quite left skewed. So we will be using IQR to identify the outliers under X2 column now. Well, to identify the outliers, let's first draw the box plot using the box plot method of Seaborn library. This is the same box plot that we have just discussed in detail. Now we need to calculate the values of this lower whisker and this upper whisker. And from this box plot, if we visually see, it appears that the lower whisker is a negative value just below 0, while this upper whisker is a little less than 2.5. Excuse me. The weather is very dry and I am having a sore throat as usual. Okay. Well, let's calculate the IQR, for which we need Q1 and Q3. I'm using the quantile method of the data frame and passing the method 0.25 for calculating first quartile and 0.75 for calculating the third quartile. And of course, the difference of these two quartiles, that is Q3 minus Q1, will give us the IQR. Let me execute. So the IQR is 0.819. Now we have the IQR. We can calculate the lower and the upper limit, and that can be done using this formula. So the lower limit is Q1 minus 1.5 times IQR, while the upper limit is Q3 plus 1.5 times IQR. Let's execute. Great. So the lower limit is minus 0.9 roughly, and the upper limit is 2.36. Okay, so we have the lower and the upper limit. It is a piece of cake now to find the outliers. Well, any value under the X2 column that is less than the lower limit, any value under the X2 column of the data frame that is less than the lower limit can be considered as an outlier. Let me execute it. So it's empty. And of course, there are no outliers. And the same was observed over here in this box plot. Good. Let me check out the outliers on the other end, which are greater than the upper limit. Great. So we have 180 rows, 180 outliers under the X2 column. So these are the outliers. You can observe that these values are greater than 2.3. Since we have a total of 10k rows in our dataset, so removing 180 rows out of them just make 1.8%, which is fine, I think. So we can do the trimming. This line of code will create a new data frame, new DF. So once I execute it, note the 180 rows have been dropped and the new size is 9820. Let's draw the histogram and box plot of the original data frame X2 column and the new data frame's X2 column. Let's execute. Great. You can observe minor changes in the distribution. This is the distribution before dropping the values, and this is the distribution after dropping the values. The data values above 2.3 are no more there in this data set. Moreover, the box plot over here, you can see there are quite a bunch of outliers, but over here we have almost no outlier. Okay, so the second technique is capping or winsorization. So instead of trimming the outliers, we can do capping as we did in the Z-score method as well. So once again, I'm using the where clause. So this code we have discussed before. Let me execute it. No change in the number of rows. Let's compare the results again. Well, in this green histogram of the new data frame, you can observe this peak over here at the upper limit value, which is due to capping. This right box plot also shows that all the outliers have been treated now and there are no more outliers as per this box plot. Great. My dear students, we are done with handling outliers using the z-score as well as the IQR method now. Let's move ahead and move on to the third approach, and that is the percentile approach. Remember, if the data is normally distributed, we use empirical relations of normal distribution, which says that all data points which fall below uh, mu minus 3 sigma or above mu plus 3 sigma are outliers. For skewed distribution, we used IQR proximity rule, which says that all the data points which fall below Q1 minus 1.5 times IQR or above Q3 plus 1.5 times IQR are outliers. And for other distribution, we use percentile based approach, where we specify a particular threshold or percentile value below and above which all data points are considered as outlier. And this is shown in this image over here. And remember, we always maintain symmetry on both sides. That is, if we remove or cap 1% data values from the right, then we also remove or cap 1% data values from the left as well. Okay, let's once again load the same dataset from the outliers.csv file to practically understand percentile method to identify the outliers. Let's visually see how the data is distributed this time under the column x1. I'm detecting outliers from the x1 column again. So this is the histogram and this is the box plot. You see in the box plot you can see we have outliers on both sides this time. Okay, so and let's suppose that we decide that all the values that fall above 99% and below 1% should be considered outliers. So I'm using the quantile method of data frame on x1 column and passing the method 0.01 for calculating the first percentile and 0.99 for calculating the 99th percentile. Let me execute this. So the lower limit comes out to be 6 and the upper limit comes out to be 53. Value 6 is of course the first percentile. That means 1% data values are below 6. Similarly, this 53, this value 53 is 99th percentile. That means 99% data values are below 53. Okay, so now what to do with outliers? The same old task. Let's trim them. So we have trimmed them. Let me compare the results. Great. You can see the distribution, you can see the box plots before and afterward. Well, my dear friends, we are done with univariate analysis to detect outliers or anomalies in our dataset. We have also discussed that these outliers may be useful for our machine learning models when the objective is to do anomaly detection. For example, fraud detection or detecting anomalies in a maybe manufacturing pipeline. Anyways, we use multivariate methods to detect outliers that only show up within combinations from two or more different variables. And there are a bundle of methods that you may come across in literature like depth-based methods, distance-based methods, density-based methods, and Mahalanobis distance-based methods. However, to keep things simple, in today's session, we will use scatter plots to visually identify the outliers. And let me once again load a sample dataset for this task. And this time I am using Ames housing data.csv file. Let me load it. So this is a big data set having 81 columns, 80 input features based on which we need to train a machine learning model to predict the output label. And that output label is, of course, sale price of the house. The dataset has 2930 rows. Okay, since we want to do multivariate analysis, so let's check out the correlation values using the CORR method of the data frame. This is a huge data frame showing all the correlation values. But I'm interested only in the correlation values between the input features and the output label sale price, and not within the input features. So I can do that as well by using this sale price with the correlation method. Great. So this now shows every single input feature of our data frame, how it is correlated with the sale price. So these all are positively as well as negatively correlated with the sale price. We can always sort it out to have a better understanding of that. So these are the sorted values now. And over here you can see that the sale price is perfectly correlated, of course, with itself. And this overall quality feature of a house has the highest positive correlation with the sale price. And this living area, the ground living area feature also has a correlation value of around 0.7 with the sale price. Let me plot a scatter plot between the overall quality and sale price of a house. So this is a scatter plot. I am using it between the overall quality input feature and the sale price. Let's execute it. It doesn't look like a typical scatter plot. This is because probably the overall quality has a rating from integer value 1 to 10. So these dots actually represent houses having an overall quality rating of 1, 2, 3, 4, and so on. By visually seeing this, we can detect some outliers. Consider these three dots. This one dot is at the quality overall quality value of 9, and these two dots are above the overall quality of 10. They appear to be outliers because a house having an overall quality rating of 10 should not have a sale price of less than 200,000. You may think of these 2 points where my mouse is hovering right now at the very top over here to be outliers as well. But I think these are not, because these might be very large mansions or houses having extremely high quality, and that's why they are having a very high sale price. And what does not really make sense are actually these three dots or houses having an overall quality rating of 9 and 10 but being sold at a much lower price. Okay, so let's go ahead and check other features like let's say, let me draw a scatter plot now among the ground living area and the sale price. Great. If you closely observe this scatter plot, you can identify the same three houses probably, which are identified as outliers in the previous scatter plot as well. These 3 points are having a large living area, a bigger living area, uh, but having once again a very low price, less than 200,000. Note that these three houses have a ground living area greater than 4,000 and sale price of less than 200,000. Now we have an idea of the outliers by seeing these two scatter plots. One scatter plot is between the overall quality feature and the sale price, and the other is between the living area size and the sale price. It's time to get the exact data or rows that pertain to these three houses. And this line of code is doing that job for us. So I want those rows of the data frame where the living area value is greater than 4,000 and the sale price is less than 200,000. Let me execute. So these are the three rows, the data of the three houses, which we have detected visually above as well. Let me get the three indices, which are 149821802181. We can get the indices using the dot index attribute. So these are the three indices. I have kept those three indices in this list. And now I can use this to simply drop these three rows from the data frame along axis 0, of course. And if we check the shape is 2927. So this new data frame has 2927 rows instead of 2930. Okay, so finally let us draw the scatter plot again of this new data frame, the living area and the sale price, let's suppose. Great. So you see, now it appears that we have cleaned the dataset, as the three outliers which were somewhere around here are no more being visible. And obviously, you could continue to explore this more, including more features and removing more houses that appears to be outliers. So I've just given you a kickstart on this. You can do this at your own time. And for this session, I think I have given you a reasonable foundation about outliers, different ways to detect and remove them from your dataset. Okay, so that is all for today's session. Hope this was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.